Hey, Vlad here, devinside.com. Welcome to another video. In the previous video, we talked about the secret weapon of object orientation, inversion of control via subtype polymorphism. And in this video, we're going to talk about inheritance, and I separated these two topics into two dedicated videos because usually these topics are introduced together, which leads to beginners not being able to distinguish between them, which is less than ideal to say the least. But that's not going to happen to you. You're lucky because you're here. All right, let's get started. As always, we're in the virtual machine, and we have Sublime running on the left, and we have a terminal on the right, which runs SPT, which runs our code. So today we're going to start with the same example as we had in the previous video, the devices and the energy meter. So this time we're going to separate them into different files. So I'm going to create a file called energymeter.scala, which is over here, source main Scala, energymeter.scala. And over here, we're going to have our class energymeter, which is exactly the same as in the previous video. I'm just going to type it out real quick, energymeter, and it accepts a device. And a device is going to be in a separate file as well, device.scala, and a device is a trait. Right, and now it should compile because now it actually exists. And what we can do with a device is we can retrieve its watts per second, how many watts it consumes per second, and we can turn a device on. And we can also, in fact, let me put it on this line. We can also turn it off like this. All right, so an energy meter takes a device, and what it can do is it can start measuring. Actually, let me remove that. All right, start measuring, and it returns a unit. And it can also do the same thing. I mean, basically the opposite. It can stop measuring, right? Stop measuring. And the first thing that it does is it turns the device on, turn on, and it turns the device off, like this. Okay, so when it turns the device off, it can capture the duration in millis, how long it ran. And again, we did the whole example in the previous video, so I'm just typing it out basically because I didn't want to copy paste it. So we capture the current time, and we subtract the turned on at millis, which is a variable that we're going to have over here. It's going to be private to the scope def like this, and it's a long, and it's going to start with a 0, and we set it over here. When we start measuring, we set it over here to system.current time millis. And then because we measure how many watts we consume per second, we have to convert it to seconds first, because this one is in milliseconds. So we have duration in seconds, which is duration in millis converted to double first, and divided by 1000 milliseconds, because there are 1000 milliseconds in 1 second, right? And then what we do is we have what's consumed in total, and we add to it whatever is currently in there, plus device dot what's per second multiplied with whatever we calculated over here. So now all that is left to do is to introduce this variable over here. For that, we can just duplicate this one, replace the name, and it's a double, right? And we want it to be able to access it from the outside. So we're going to do this, which is going to be a getter. And I forgot an underscore here. Let's have an underscore here. And now the setter is going to be private, exactly as in the previous video. It's going to be called what's consumed in total, and very important, underscore equals, and it gets a new value, which is a double, does not return anything useful, and all it's doing is it's just setting it what's consumed in total equals new value. And I believe that's the entire example. All right, so there's one typo over here, and I'm sort of used to starting with making things as defs, but these two are obviously vars. There, whoops, there we go. So now everything should be fine. In the previous video, we also had two devices, so let's add them. So we had a TV.scala, all of the files are over here. Okay, so it's just a class TV stands device. And actually, let me do this and put the device over there so that you can see what we're doing. So we can override a def as a val. So we just take the watts per second over here, which is an integer, and for a TV it's a 500. I'm just using the same numbers as in the previous video. I don't actually know that a TV consumes 500 watts per second. And we override def, and we can just copy paste that, turn on, which just prints out TV on because it's an example for educational purposes, right? In an actual application, would actually literally turn some TV on, okay? And turn off looks like this. And we also had a light bulb, which is going to look exactly the same. So I'm going to just copy paste that. I'm going to create a light bulb, and we're going to paste that, and we're going to call it light bulb, and we're going to say over here light bulb on, light bulb off. All right, so we have them both now, and now we can finally return to main and create an example that works with this. Okay, so the first thing is that we're just going to create a bulb, which is a new light bulb. Let me remove the cursor. And we're also going to create a TV, which is a new TV. Hold up, yeah, the light bulb actually consumes only 100 watts. I forgot to change that. All right, so we have a bulb, we have a TV, we have a meter, which is a new energy meter, and let's give it a TV. It doesn't really matter in this case. And we're going to do meter start measuring, then we're going to hold up for a second, literally, and then we're going to do meter stop measuring, and then we want to see how much we consumed, what's consumed in total. And then we're going to have an empty line, and then we're going to do the whole thing again real quick, same as we did in the previous video. So right now, if I didn't make any typos, we should be at the same stage as in the previous video. So if we do this with a TV, we have 500 and something close to 1,000. And if we use the bulb, then we should have something like 100 and 200. Let's see. And yeah, it's fine. Now in this video, we're just going to start improving the code a little bit. Because, for example, right now, if you look at the light bulb or the TV, because they actually look the same, we can, for example, turn it on multiple times, right? It's just gonna, you know, print out this thing. We don't really have to, you know, I don't really have to go to main to demonstrate that, right? And also, if it's turned on, then we can turn it off, and the energy meter won't even notice anything like this. So the first step that we're gonna do is we're gonna improve the light bulb. We're gonna make sure that it's only possible to turn it on if it's off, and it's only possible to turn it off if it's on. And also, as we will see very soon, as a byproduct of that, we will also be able to ask light bulb if it's on or if it's off. So let's improve turn on. So let's just do exactly what I just said. So it should only be possible to turn it off if, to turn it on if it's already off. So let's do something like if is off, well then set some internal state, right? So we can do is on equals true, and otherwise let's just explode system error already on, right? And let's do a similar thing over here. So we can say if is on like this, then let's turn it off by setting is off to true, otherwise let's explode as well. Already off, right? So as of right now, it shouldn't compile because we don't have methods is off, and we also don't have variables is on and is off that we can set them. So let's implement that first. So everything is going to be controlled by just one variable. It's going to be private because we only want to be able to mutate it from the light bulb, right? It's a variable called is on, which is a boolean, and by default, when we construct the light bulb, it's going to be off by default. Okay, so now we're going to have a setter for this. We're going to have is on like this, same as before within the energy meter. We're going to have a new value, which is a, what's wrong with me today, which is a boolean. Doesn't return anything useful. All it's doing is setting is on to the new value. And also I forgot the setter because we want the setter to the getter because we want it to be beautiful as well. We're gonna have a def is on, which is a boolean, and all it's doing is it returns is on. And we're gonna do the same trick was is off. Actually, we're gonna copy and paste that, but we don't need a separate variable. It's enough to have only this one variable is on. Okay, so basically everywhere where it says is on, it's gonna be is off equals not is on. So it's this one, which basically just returns the value of is on, and then we negate it. And then when we set is off, all we're doing is we're setting is on to the negation of the new value. And I believe now it's actually done. Yeah, so it works as before, so we can turn the light bulb on and off. But if we go back to main, let me not have this. Okay, so let's try to do. So we have a bulb, and by default it's turned off. So when we create it, it is already off. So actually we can do print line bulb is off, and it should return true, right? So it's true. So because it's off, if we try to turn it off, turn off, it should explode, right? It should explode. It should say Java long runtime exception already off, and this is happening because in the light bulb, when we're trying to turn it on, it says, okay, is it off? Well, no. Therefore, we're going to throw this exception. So this is exactly what's happening. Let's play through a few other scenarios where which should also not work. For example, it should not be possible to turn it on twice. So once should work, but twice should explode. It should say, hey, it's already on. Now that's kind of cool, and the benefits of that are kind of obvious, but still, let's enable our old example. And so as of right now, we're playing with the bulb, right? So if, for example, if we, I don't know, if we stop measuring twice for some reason, I don't know why, then it should prevent that, because it's going to say, hey, it's already off. There's no point in turning it off again. Look what's going to happen with the TV, because the TV doesn't have that functionality yet. Let's see. So the first time everything is fine, but then the calculation is actually wrong. So what is happening is that stop measuring is not only stopping the measurement, it actually notices the current time. So it basically adds these 500 watts again, which is maybe a topic for a different video, how to improve that. But basically, let's go to the energy meter for a second. So basically, when we call stop measuring, it just assumes that the device was on before, right? So it doesn't do any checks. It just measures the current time and just adds it. It doesn't care if it was on before or not. All right. So let's go back to main and let's fix that real quick. And now the question is, how do we make sure that the light bulb and the TV are both safe without duplicating the code, right? Because we already improved the light bulb, and the light bulb is kind of perfect. But now if we wanted to improve the TV the same way, we would basically end up copy pasting the entire code and just, renaming light bulb to the TV, basically. That's all. And this is where inheritance comes into play. Now, inheritance, which is the topic of the current video, it can be used to reduce code duplication, but lately the entire industry is kind of frowning upon that. So people tend to favor simple composition over inheritance, which is probably a topic for another video, but we basically did something similar in the previous video. Remember when we were developing this whole subtype polymorphism example, we used to have methods called toDevice, which was defined on a light bulb and on the TV. This was sort of the notion of composition instead of inheritance to reduce the code duplication. But in any case, this video is about inheritance, so sometimes it is actually useful, sometimes it's actually not too bad. So let's start there. Whereas in subtype polymorphism, which was the topic of the previous video, we wanted to define some abstract methods on the base type with the sole purpose of being able to override them in the subclasses. Inheritance does it sort of the other way around. It still has the methods on the base type, but they're not abstract, they're already implemented, and their purpose is basically to use them in the subclasses. So usually subclasses don't want to override them, they just want to inherit them, so they just want to have access to them. In order to start with that, we're going to cut out is on and is off, because every device can be asked if it's on or if it's off, right? We're just going to cut it out, and let me save that so it's not going to compile, and we just go to the device, which is over here, and we're just going to paste it over here, right? Now, because it's private, the light bulb is still not going to see it. So it says is on is not a member of light bulb. And there's another keyword that we're going to learn today, which is called protected. So if we replace private with protected, then everything still should be fine. So now, even though the TV does not have methods is on and is off, because it extends the device, we can actually call them. So if we go to main, and instead of doing that, we're just going to do println TV dot is on, and it's still going to work, right? Because the TV all of a sudden has access to this method, and the light bulb still has it as well, right? Because both of them extend the device. Sorry, why did I say light? Okay, there we go. Bulb is on. All right, so let's revert it to our actual example. All right, so the next thing that we're going to do is let's look at the light bulb, and let's try to do the same with turn on and turn off. But before that, we actually have to notice that it is a bit different, right? So even though it looks very, very similar, a light bulb actually says light bulb on, and a TV actually says TV on. So before moving turn on and turn off from the light bulb to the device, let's just for now at least copy them to the TV so that our TV is also improved. So let's just replace them over here, and instead of light bulb, we're going to say TV. Now we have a problem, and this is also the reason why programmers don't like duplication. Now it's super easy to break a light bulb, for example, or the TV, but the other one is still going to work, right? Which is going to lead to something like your users coming to you and saying, hey, we're using this light bulb and it works just fine, but then every time we take the TV, then it's broken. Like, what's up with that? So let's demonstrate that. So for example, if we turn, let's break this one, for example, in the TV, instead of saying true here, we're gonna say false. Let's see what's going to happen, and we're actually using the TV. So now all of a sudden the TV is already on, because over here we're trying to turn it on over here by start measuring, right? Because the meter is going to turn it on, but the problem is that stop measuring didn't turn it off because there is a bug over here. Before fixing that, let's reverse it. So what we're going to do is we're actually going to finally copy paste turn on and turn off to the device. Right over here we have turn on and turn off. So instead of them just being abstract methods, they should be actually implemented methods. But we're not going to do this println, right? So it's the same as before, but we're not going to do the println, right? And now what we're going to do in the TV is we're going to, the same as we can call methods on the current instance, and the compiler inserts this keyword for us. So for example, if from turn on we would want it to call turn off, we can do it like this, right? But we can also do this dot turn off. So what we have with inheritance is we have yet another keyword called super turn off, for example, and this will cause the compiler to make it in such a way that we're not calling this override of the turn off, but we actually call it on the base class. So we actually call it on the device. So in this case, we would call this turn off, and we're gonna make use of that. So the turn on, all it will do is it will call the super dot turn on, and then similar to as it was doing before, it's just gonna say, okay, so now the TV is actually on. And the same thing over here. So we're gonna remove everything except for the print line TV off, right? And we're gonna say super dot turn off, and the TV is now off. And now all we need to do is we need to fix the error that I just made in the device, because we're not overriding them over here, we're just defining them, right? And now we have the TV, and we also need the same thing in the light bulb. Let's go to the light bulb. Let's do that over here, light bulb, and it should say light bulb like this. And also, let's, in the main example, let's just for fun, let's start using the light bulb now, just to mix it up a little bit. All right, the bulb, and we have a 100 and we have a 200. And the next thing that we should notice is that our clients are the ones who implement the devices, right? So in this case, it's the light bulb and the TV. They still have like a bit too much power, right? So they can still make a mistake over here. So for example, they could still forget to turn the TV off, right? And now we're going to have the same problem as before. So the first time it worked, we turned the light bulb on and then we turn it off. But the second time we tried to turn it on, the problem was that it wasn't really off before, even though we called turn off, right? So there's a way to fix that. By the way, as of right now, I hope you're noticing the pattern in all of my tutorials. Like usually I present a problem and I try to fix it by improving the code bit by bit, and thus reducing the possibility, reducing those traps that my fellow developers and I could fall into. And if you keep this sort of mentality in mind every time you write code, this will for sure improve the developer inside you, which is what this channel is all about. And another tiny thing about this keyword super, there's a concept called open recursion, which explains properly how this super works and how this works. But as of right now, I'm trying to create this whole Scala playlist by giving you basically the minimum of what you need to get started with building big programs as fast as you can. So explaining concepts like open recursion is not entirely necessary, I believe, but I'm sure that one day I'm going to create a video about that as well. All right, so we're in the middle of fixing this problem. So what we want to have is we want our clients to feel as safe as possible. So we want to implement as many invariants in the device as we can, so that the clients have less area for making mistakes. And there is this famous book called Design Patterns, Elements of Reusable Object-Oriented Software, which is also known as the Gang of Four book because it's been written by 4 authors. This book is simply a catalog of patterns. There are like around 80 patterns or so. And in this particular example, we're going to use one of them called the template pattern. The idea is to use the device as a template for all the classes that will extend for it. And the idea is to make sure that we forbid our classes to override certain things, and we make sure that certain things are being called and so on. So these things are called invariants, and we wanna make sure that the invariants are being kept in check in the device and not in the light bulb and not in the TV, just in the device. By the way, this sounds very, very similar to higher order functions. Remember, if we do something like this, let's just do hello world for each print line. It's a very, very similar pattern, right? So in for each, there is already a part of the algorithm that knows how to walk through the string, and it doesn't matter what it's going to do with every character. This is the part that can be injected, right? Injected into the template. So there's already a template that knows exactly how to walk through the string. So there's no way that by injecting this algorithm, I can break the walking through, or which is also known as traversal. There's no way that I can break the traversal of that string. In fact, we've seen in a few videos ago about, in the video about higher order functions, and especially in the video about function currying, how functions basically become classes when they grow up. In this case, it's subtype polymorphism that is being used here, but as of right now, I haven't explained properly how function literals are implemented in Scala, right? So you don't really see that, but basically, whatever we have to inject into for each has to have the form, subtype polymorphism. It has to have the form of a function that takes the character in and does not return anything, right? So it returns a unit. So a lot of patterns in this design pattern book are actually, they can be implemented with higher order functions. For example, there is the strategy pattern, can be implemented with higher order functions. There is the command pattern, can be implemented with higher order functions. There is the template pattern, can be implemented with higher order functions, and so on and so on and so on. So the template pattern basically mixes subtype polymorphism with inheritance. So the idea first is that when we go to the TV, for example, that we extract this sort of ad hoc functionality. By the way, there is a space missing over here. This ad hoc functionality like this, right, into a dedicated method. So we're going to have a private this def actually turn on, same signature as turn on, right? That will do this. And remember, in an actual example, it will actually turn the TV on, okay? So now instead of just calling print line TV on over here, we're just gonna call actually turn on, right? So it's basically, for now, it's just a refactoring, and we're gonna do the same thing with turn off, right? So on is becoming off, like this, and we just replace this one with this one, right? And we're gonna do the same thing for the light bulb in a second, actually. Or actually, we won't need to, because we're gonna move this to device as well. So the idea is basically to move the signatures of actually turn on and actually turn off into the device. So let's do that. So if you copy that like this, and we put it into the device, which is over here. Let's put it over here. This is the turn on, and this is the turn off. Now, as of right now, it's not gonna work, right? Because they're private. So we can do the protected trick again, protected, and it's still not gonna work because we're overriding in the subclass of the TV. The actually turn on is less visible that is in the device, which is unacceptable. So we have to do protected, and I prefer to use the override keyword. So we use the override protective def, protective this def actually turn on, and now we have to do the same thing in the light bulb. Okay, so if you go to the light bulb, let me just copy that. We go to light bulb, we put it over here, and this should say light bulb, light bulb, come on, light bulb, and we do the same with the off one. Turn off, off, and now it works again, right? And it somehow also does the actual thing. In the light bulb, notice that we forgot actually to call it. So let's call it over here. Actually turn off. We'll call it over here. So as of right now, we sort of copy pasted some code around, but we haven't actually changed much. So as of right now, when we call turn on the light bulb, it goes here and it calls the super turn on the device. In fact, let me put the device down there over here. So again, so we call turn on the light bulb. It calls super turn on the device. On the device does this whole dance, right? And then we come back and we call actually turn on. So the idea here is that the device should do that, right? So the device should call actually turn on, and the device should call actually turn off over here, right? So as of right now, we just need to remove this from here and this from here, because this is already happening. You see, and now we're doing it twice, right? And now the same thing for the TV. So we just need to remove the actually turn on, and we just need to remove actually turn off. And now notice that the only implementation of turn on and turn off that does not introduce a bug, so basically the only valid implementation of turn on and turn off is basically just to call the turn on and turn off on the device, right? So on the base class. So there is a way to improve this even further, right? Because now our clients, they still have an option to make a mistake, and we don't want that. So the way to prevent the possibility of overriding something is by using the keyword final. So if you go to device, and we're gonna go to turn on and turn off, and we're gonna make it final, which again is the goal of the template pattern, right? Now the compiler is gonna complain. It's gonna say, hey, turn on cannot override a final member. So basically, we just need to remove it because it's already happening in the TV and in the light bulb. Remove the turn on, remove the turn off, right? So now all the code duplication is gone. It is very hard to make a mess in the light bulb or in the TV, because most of the code is already in the device, and it makes sure that everything is being handled properly. Okay, and let me show you two things as well. First of all, the device sort of trusts the clients a little bit, right? Because, for example, right now we're using a light bulb. What's going to happen if instead of doing this, we're actually going to do something like programmer mistake, right? So now, I was hoping that I would say that the light bulb is already on. In fact, the light bulb is already on, right? Because it did this. So the light bulb is in the on state, and only then it exploded. So maybe it's not ideal. So maybe we should actually, we should just turn it on first and then set it to true. But this is a topic for another video. This is a topic about, proper object-oriented design, and in this case, it doesn't really, matter much. So another thing that I wanted to show you is that you can not only have the same visibility when you're overriding methods, you can actually increase it. So for example, you could just override this like that, right? So now all of a sudden it becomes public. Everything still works, and everything is still kind of safe. So you can, if you had an instance of a light bulb in your hand, you can call actually turn on it. But if you have an instance of the device, like what's happening in the energy meter, you still can't turn it on, right? So if you're in a device over here, and let's try to do actually turn on, it's going to say actually turn on is not a member of device. Yeah, exactly. It is, however, a member of the light bulb, right? So it's possible to call it on a light bulb, but it's not possible to call it on a device, which is usually what is happening in big systems. Usually you're going to have devices floating around, and algorithms like energy meter that work with devices instead of working directly with light bulbs. It's inversion of control, or with other words, it's called an indirect transfer of control, right? Okay, so let me remove that. And we're going to have our example again. Let's also revert that like this. Okay, so everything is back to normal now. Now let's review the code a little bit. So we have the device, which is, it's very beautiful. It has the is on stuff over here. Let's actually do here. So we have the is on methods. We have the is off methods. We have the turn on methods, which is this one and this one, and we have the turn off methods, which is this one and this one. Now it's very clean now, right? So the device is clean, the TV is very clean, the light bulb is very clean, the energy meters are very clean because it works with devices, and it just turned the device on. And if it's if it's already on, then it's just going to explode, which is it's not the ideal design, but it's better than introducing an inconsistency with the watts consumed in total, as we had before. And our main is also very tiny, very shiny, very clean. Maybe what I should do now is to maximize Sublime and split it like that, so that you can see a TV, for example, on the left and a device on the right, and you can sort of see how they interact with each other, right? So for example, if you have an instance of TV in your hand and you're calling turn on, right, it goes straight to here. It checks if it's off. It switches the variable of is on to true. Then it calls actually turn on, which is an abstract method over here, doesn't have an implementation. The compiler will make sure that there will be an implementation. Otherwise, it's not going to. Otherwise, the TV is not going to compile. So at this moment, it calls this functionality. It says print line TV on, which is dynamic dispatch again, as in the previous video, right? So this part is not inheritance. This part is subtype polymorphism. As I already said, the template pattern mixes them both, and which is also the reason why inheritance and subtype polymorphism are usually introduced together. But then again, then people end up not being able to distinguish them, which is not good. So this completes this whole example. So now you know enough things about inheritance and subtype polymorphism. We're not done with it yet. We're going to continue with in the next videos with it. As of right now, I'm just going to introduce a few keywords that just didn't fit into this example, but are still really important. So what I'm going to do now is I'm going to have only one pane, and I'm going to create a new file, and we're going to work in here. Oh, actually, one more thing between the difference between subtype polymorphism and inheritance. So subtype polymorphism is more about the types, right? So if a class TV extends a device, it means that every TV is a device. So for example, a real life example, if you say, hey, my TV is broken, do you know anyone who can fix a TV? So, well, I don't know anyone who can fix exactly a TV, but my uncle has a repair shop and he can fix absolutely any device, right? So it's about the types. And by the way, remember when we talked about the environment model of computation, we said that its purpose is basically to, not its purpose, but the way it's doing is it maps an object in real life to a computational object, which sounds very, very natural. So this my uncle has a repair shop example is a perfect example for that, right? So it's very, very natural. Inheritance is rather about the classes instead of the types, as we just learned. So it's basically a way to access a method that is defined on the base class from the subclass. In a sense, subtype polymorphism is about looking down on your type hierarchy, right? So you can say, hey, I have a device, but if you give me a TV, I'm just going to call methods on the TV. And inheritance is sort of the other way around. It's about looking at the type structure from the bottom, basically on the class hierarchy from the bottom. So you're going to say, hey, I am a TV, but I also inherited functionality of a device. So semantically, these two concepts are sort of fundamentally diametrically opposed, right? But syntactically, in most languages, they look very, very similar, and this is why many people confuse them. All right, so as we've already seen, there are a bunch of keywords for changing the visibility, and I'm just going to list all of them over here. Private this, which means only current instance, and let's switch syntax to Scala. All right, so private this means only the current instance. Then we have just private without the this, and it means that any instance of current class can access it. Now we have protected this, and by the way, you don't only have this, right? So if you have, for example, an object A, and then inside of it you have a class B, for example, then you can say, okay, it's private, but not only to this instance, and also not only to the class B, but also to the entire object A, right? So let me just type it out. So if you have object A, and in here you have a class B, and inside of it you have a method M, right? Like this, which is just saying I'm M, right? So you can also do private instead of, so you can do this, right? You can do private, which means to B, but you can also do private A. I believe this should work. In fact, let me actually try before I'm saying something like this. Let's go here. Let's put it over here. Let's see if it compiles. And yes, it does. Yes. All right. So now I'm actually sure. All right. Let's go back. Let's remove that. Let's go here. All right. Let's remove that. So we have protected this, which means that only current instance and the subclass instance. Whoops, I didn't actually want to save it. Right, and then we have protected without any modifiers, right? Which means any instance of the current class and any instance of any subclass. Now, when you're in Java, you also have the public keyword. Scala doesn't have the public keyword because basically if you just leave either private or protected out, then the default visibility is public, right? And it's also known as the public API, whereas APIs I usually public anyway, right? So an API means an application programming interface, and the links to the APIs of the Java standard library and the Scala standard library are going to be down in the description. We've also seen some keywords for inheritance. Let's do them over here. So we have final, and it always depends if it's on the class or on the trait or on the method. So if final is on a class, means that it can be extended, which is why case classes should be defined final, right? Because you don't want to extend from case classes, but more about that in a different video. And also a final class cannot have abstract members, because a regular class also can't have abstract members. Only abstract classes or traits can have abstract members. So final, come on a trait is not allowed, because a trait is basically something like an abstract class. A final on any member means can't be overridden, right? And now if you don't have anything, right? So I don't know, we can say let's do something like no keywords, right? That if it's on a class, it means that it can be extended, but as the same as over here, it can't have any abstract members. So nothing on a trait means that it can be extended or actually mixed in, right? And nothing on on any member means can be overridden, but it doesn't have to be. There's no way to enforce it. So abstract, I sometimes say abstract. So abstract on a class means must be extended. In fact, that's not true. Abstract does not mean that it must be extended. It means that it can be instantiated. Can be instantiated directly, right? So it can only be extended from. Now it can be used on a trait, but it means basically the same thing. Basically, traits are always abstract traits, and also it can have both abstract and implemented members, right? So only because the class is abstract, like in the case of the device, actually, it can still have implemented members, even final members, right? let's continue. So we have abstract on any member is not allowed. So if you want to have an abstract member, basically all you need to do is to leave the equal sign out and to leave the body, right, as we discussed in the previous video. So if there is no keyword, but there's also no equal sign and no body, it means that it must be overridden. Now there's also a keyword called sealed, which means the same as final, and you can only seal traits or classes. I don't think that you can seal methods actually. Yeah, so it basically means the same as final, so you can't extend it, but you can extend it if you're in the same compilation unit, and usually compilation unit means in the same file unless you're doing something very, very exotic. Now, the last thing that we're going to do is the combinations. So everything except for obvious things is basically okay. So you can't have, for example, final abstract, right? Doesn't make any sense. As I already said, you can't have a final trait, and also you can't have a private abstract on any member. Basically, you can't have a private abstract def, for example, or private abstract val, or something like this, right? It's not possible. And also the order of them also doesn't really matter, but I prefer to use this order. So final first, then override, then protected, then this, and then def. So this is the order I prefer, but you can do whatever you want, right? So for example, you can say override final protected, something like this. Right, and also you can leave them out as well, right? So you can do override final, whatever. But I prefer this order. It kind of reads nicely. It means that you know, there might be like a few overrides in the whole tree, but this is the final one, right? And what you're overriding is a protected def, right? So it kind of makes more sense. So I prefer this order, but you know, it's a kind of a taste thing. So agree on something with your team and follow that. All right, I hope you like this video. That's all I have for you today. But as I already mentioned, we're not done with inheritance or subtype polymorphism, actually by a long shot. We're still going to have a bunch of videos about them. So I hope you liked it. Subscribe if you're new here and if you want to improve the developer inside you. And yeah, that's it. Cheers. Take care.